Hello again, this is Galen Pickett, Cal State University Long Beach, Physics 151. So I do want to talk, in Chapter 9, there is this very important distinction made between what does the point-like system or the complex expanded system tell you about how applications of the energy principle and momentum principle work. So this is not something which changes the nature of the energy principle or the momentum principle. It is another idea we use to apply these principles and get information from systems. So here's the situation that I've got. I've got a stick that's initially at rest. There's a mass m on one side of the stick, a mass m on the other, and I'm going to grab each stick and I'm going to use a force F, and I'm going to move each of those objects along the radius of a circle. So these two objects are going to be spinning around a common center. They're connected by a rigid stick of length 2r, and I'm going to grab a hold of this object and move it all the way around once. I'm going to grab this object and move it all the way around once. And the question is, how fast is each object moving? After I do that. So I want to characterize that with energy and momentum as well. So let's think about what is the change in the momentum of the system. So I've got two objects here, and let's say that it takes an amount of time, delta t, in order for this process to happen. Well, you could say to yourself, well, shouldn't the momentum of this system, I've got a force, I've got a delta t, shouldn't it just be F times delta t to find out what is the change in the momentum of the system? And that is incorrect for a couple of reasons. The force that I use on any one of these objects has a constant magnitude, but it does not have a constant direction. Once the stick has moved over to this position, now the force I'm putting is going off in these two other directions, which are perpendicular to the stick. So just using that force is not going to be sufficient here. But let's take a look at what this, even more significant, the total force from the surroundings. The way we use the momentum principle, it is the F net, the total interaction from the surroundings. And if I look at these two forces, when I start off, I have one force pointing upwards and one force pointing downwards. So F net is equal to 0 when t is equal to 0. At this time right here, when the stick is off at about 45 degrees, I've got a force which points up in that direction. That's on this top one. And I've got a force which points down. That's this one. Again, it's equal to 0. So if I make a net force diagram, there is the system. When you do use the momentum principle, all the matter of the system is combined into one particular spot. So I've got two masses, they're sitting right there, and at this particular time, I've got one force like that, one force like that, and that adds to 0. So the change in the momentum of the system is equal to 0. And that's not surprising. The center of this stick, because of the way I set this up so symmetrically, the center of the stick does not move. So the net force from the surroundings, the F net, is 0 at all times. Well, let's see what the energy principle might then say. So the change in the energy of the system is equal to the work from the surroundings. I just got done saying that the net force from the surroundings is 0, so should not the work from the surroundings also be 0? Which would say that the change in the energy of the system would be 0, which would mean that the two objects are standing still. And that is why we need this point versus complex system. Once I'm done doing this, these two, it's a frictionless surface. I grab these two objects, I set them spinning. After my hand lets go, for t greater than delta t, I just have this two-stick system, this two-ball system, and it's spinning forever. It's got some velocity like that, some velocity like that. Each of these two objects has got some kinetic energy. So this is what the point system tells you. The point system, you take all the mass concentrated at the center of mass, the center of mass of the system, and then all the forces act at the center, at that center, at the center of mass. And now, for this point particle system, the change in the energy of the system is equal to the work from the surroundings is something that will tell you this fictitious point particle. In our system, I've got k initial is equal to 0. For this fictitious point particle, my final state, I've got k final is equal to 0. What this is telling you is how is the center of the system moving? How is the center moving? And what we have, since the net force from the surroundings is 0, the work from the surroundings is 0, and the center of the system is still at rest. The center of mass is still at rest. However, I have done some work here. I've got, for these two particles, I grabbed this one right here, and I moved it a distance 2 pi r with my force F that was parallel to the displacement. So the work I do is equal to 2, because there's two objects I'm working on. I have my force, and it's a part of the force that is parallel to the motion. That's 2 pi r. So the work I do is greater than 0. And this is the work that comes into the complex system. I need to see where is the force being applied. And for this case, I can see that the two objects are separated like so. There's a work there, there's a work I'm doing on this one, and now the change in the energy of the system is going to be the change in not how the center is moving, but how each one of these objects is moving. So I have the k for the system. And I have two masses here, so I have 1/2 mv squared. That's for the first mass, and I multiply it by 2 to get the kinetic energy that each of these things has got. So the complex system tells me that the total work from the surroundings is 2F times 2 pi r, and that is equal to 2 times 1/2 mv squared. So I could tell you how fast these objects are moving. V squared times m times 1/2 is equal to F times 2 pi r, and then I would have V squared is equal to F 2 pi r times 2 over m, or V, the speed with which any one of these objects is moving, is the square root of 4 pi f r divided by m. This is the internal kinetic energy of the system. You need to use the full expanded system to find out what is the internal energy. The point system will tell you what is the k translational. This is the part of the kinetic energy that takes the center of mass and moves it from one spot to another. In our case, k translational is equal to 0. The complex system has got details like these two pieces of matter, m and m, moving with the velocity v, and it keeps doing that around the edge of the circle forever.